Quantum advantage, a new framework from IBM and Pasqal. Quantum computing is on the brink of a breakthrough. But how do we know when we've truly crossed the line from theory to reality? A groundbreaking study from IBM and Pasqal has proposed a clear, testable framework to define and prove quantum advantage, sparking both excitement and debate in the field. But here's where it gets controversial. Will this framework actually help us determine if quantum computers are truly outpacing their classical counterparts, or just creating a new set of benchmarks? The researchers argue that quantum advantage isn't about flashy claims or hype. Instead, it's about measurable improvements in efficiency, accuracy, or cost compared to classical systems. Their framework focuses on three key problem types: sampling tasks, variational algorithms, and expectation value calculations that could deliver early wins for quantum computing. However, they emphasize that progress hinges more on managing errors than on perfecting algorithms. Let's break this down. Quantum computers excel at solving problems that classical systems can't handle, but verifying their results is a major challenge. Imagine trying to prove a math problem solved by a quantum computer. How do you know the answer is correct if the system itself is too complex to simulate? The study outlines three strategies to address this trust issue: using fault-tolerant circuits, which require thousands of qubits, leveraging problem types that allow classical verification, and relying on variational algorithms that compare outputs to known values. Each approach has its pros and cons, depending on the task and available hardware. Now the real question: which problems are ripe for quantum advantage? The study identifies three promising areas. Sampling tasks, like generating random bit strings from quantum circuits, could offer big gains, but are hard to verify. Variational algorithms, such as those used in chemistry simulations, provide more modest but reliable results. Expectation value calculations, crucial for quantum simulations and machine learning, require minimizing errors from noisy circuits. While all three have potential, the researchers stress that risk and reward vary. Some tasks may yield quick wins, while others demand more careful validation. Here's where things get tricky. Errors are the biggest barrier to quantum advantage, not the algorithms themselves. Today's quantum processors are noisy, and even small mistakes can derail computations. The study categorizes error handling techniques into three tiers: error correction, the most rigorous but impractical for now; error mitigation, statistical methods to reduce bias; and error detection, identifying and discarding faulty runs. Hybrid systems, combining quantum circuits with classical post-processing, are seen as the key to overcoming these challenges. Hardware also plays a critical role. Superconducting circuits and neutral atom systems are highlighted as the most promising platforms for early success. IBM's 156-qubit Heron processor, capable of performing millions of operations per second, is cited as a strong candidate. Pascal's neutral atom devices, which can operate in both analog and digital modes, are praised for their flexibility in simulating physical systems. These technologies are already being integrated into high-performance computing environments, blurring the lines between quantum and classical computing. Looking ahead, the researchers caution against declaring any single architecture as the ultimate winner. Instead, they urge the field to adopt clear, testable benchmarks. Even if a classical method eventually surpasses a quantum one, it's not a failure. It's a sign that the field is evolving. As one researcher notes, "We expect that credible evidence of quantum advantage is likely to emerge in one of the areas highlighted here within the next 2 years, enabled by sustained coordination between the high-performance computing and quantum computing communities." So what comes next? Not dramatic declarations, but incremental wins. A quantum algorithm outperforming a classical solver for a specific problem, a noise mitigation technique pushing accuracy past known limits, or a hybrid system achieving a lower energy estimate than any classical counterpart. The race for quantum advantage is far from over, and the conversation is only just beginning. Quantum computing's three major barriers. Challenges 2025 and beyond. A quantum revolution is coming, but not without its challenges. Imagine a world where computers can solve complex problems that were previously unsolvable, and where the boundaries of innovation are pushed to unprecedented heights. This is the promise of quantum computing, a technology that has the potential to revolutionize industries and transform the way we live. But despite its vast potential, quantum computing is still in its infancy, and there are several major barriers that need to be overcome before it can become mainstream. The technical challenges. One of the biggest technical challenges facing quantum computing is the fragility of qubits, the fundamental units of quantum information. Qubits are incredibly sensitive to their environment and can easily become unstable, losing their quantum properties. To overcome this, scientists are developing new technologies to keep qubits stable, such as superchilling them to near absolute zero and housing them in vacuum chambers. However, these solutions are still in their early stages, and it will take significant advancements in technology to make them practical. Another challenge is the sheer number of qubits required to make quantum computing useful. Currently, most quantum computers have between 50 and 200 physical qubits, but experts predict that tens of thousands to millions of qubits will be needed to achieve true quantum supremacy. This is a daunting task, as it requires significant advancements in materials science, engineering, and manufacturing. The software gap. But even if the technical challenges are overcome, there is still a significant software gap that needs to be addressed. Currently, most quantum software is designed for specific purposes and is not widely available. This means that companies and researchers will need to invest significant resources in developing their own software and infrastructure to take advantage of quantum computing. The bigger picture. But the challenges facing quantum computing go beyond the technical. There are also significant societal and cultural barriers that need to be addressed. For example, there is a severe shortage of skilled quantum computing professionals, with many companies struggling. Quantum computing, the next big leap for humanity. Quantum computing is truly revolutionary. No exaggeration here. According to analysts at Bank of America, this groundbreaking technology could represent humanity's most significant advancement since we first harnessed fire. In a recent analysis, the Bank of America team had to look back through the annals of history to find a comparable leap in human innovation. The reason for this is simple. Quantum computing, which utilizes the principles of subatomic particles to process information, has the potential to propel us far beyond the capabilities of conventional semiconductor-based electronics. They boldly stated, "This could be the biggest revolution for humanity since discovering fire." Imagine a technology that can execute countless complex calculations instantaneously, dramatically accelerating our understanding and progress as a species. To put this into perspective, early humans are believed to have started using fire in a controlled manner hundreds of thousands, if not a million years ago. So how does quantum computing stack up against such a monumental discovery? According to Bank of America, there is theoretically no limit to the calculations a quantum computer can perform. This could lead to transformative changes across various fields, including the development of new pharmaceuticals, innovative materials, extended human lifespans, and enhanced security measures in data encryption and logistics. Moreover, the ongoing revolution in artificial intelligence, AI, could be significantly accelerated by quantum computing, and the two technologies may even enhance each other. Bank of America noted, Gen AI can help speed up the development and testing time of quantum systems, which could elevate AI model training to the realm of artificial superintelligence. We've already witnessed remarkable achievements in quantum computing. For instance, in 2023, Google announced that its Sycamore quantum processor completed a calculation in just 6 seconds, an operation that would have taken the most powerful supercomputer an astonishing 47 years to finish. Additionally, in December, Google revealed that its Willow quantum chip solved a problem in under 5 minutes, a task that would have taken the fastest supercomputer an unfathomable 10 septillion years. That's 10 followed by 24 zeros. However, it's important to note that, as Bank of America pointed out, no quantum computer has yet solved a practical real-world problem more quickly than a classical computer. This limitation arises because qubits, the basic units of quantum information, are still plagued by excessive noise, interference that can lead to errors in computation. In January, Jensen Huang, the CEO of NVIDIA, expressed that the most exciting breakthroughs in quantum computing are still over a decade away. He later sought to temper expectations, suggesting that quantum computing won't necessarily be a magic solution for tasks like spreadsheet calculations. Rob Schoelkolf, co-founder and chief scientist of Quantum Circuits, echoed this sentiment, indicating that advancements in quantum computing will likely occur gradually rather than in a sudden dramatic shift. We're going to be turning the volume steadily, and we can start to hear the music now, and eventually everyone will be able to hear the music, he predicted, hinting at a future where quantum computing becomes more mainstream. On another note, Bank of America highlighted the geopolitical ramifications of quantum computing. This technology has the potential to equalize processing power on a global scale, an area where the United States currently holds a dominant position. The analysts warned, whoever wins the quantum race will gain an unprecedented geopolitical, technological, and economic advantage. As we stand on the brink of this new technological frontier, it raises important questions. Are we ready for the changes that quantum computing will bring? How will it reshape our world? We invite you to share your thoughts and opinions in the comments below. Do you agree with the potential of quantum computing, or do you have reservations? Let's discuss.